blunders from, yes, the
I have
often
good news
giggly
and
Vice
bad
President
news.
Kamala
Bad
Harris,
news first.
who wants to
2
let
years ago,
us
we
know
reported on
she
the
really
crisis
likes
in
the internet.
cosmology.
I mean, really
Since then,
likes it. Take a
it's
look.
only gotten worse.
Context. Well,
And actually, the good
internet
news is also
an
that the
essential
crisis in
part of life in the
cosmology
21st
has
century.
actually gotten
Can't
worse,
get around it.
which means
Can't get
we
around
may be
without
onto
it.
something.
Biden, Kamala, and Nancy Pelosi.
The most exciting thing for any scientist is when something they thought they knew turns out to be wrong. So it's no wonder that many cosmologists are starting to get excited by what has become known as the Hubble tension, or the crisis in cosmology. The crisis is the fact that we have two extremely careful, increasingly precise measurements of how fast the universe is expanding, which should agree with each other, and yet they don't. We first reported on the growing hints of this tension 2 years ago. Back then we expected the new refined measurements would bring the numbers into agreement. So far that's not been the case. But just recently, one of these methods received a massive refinement due to the Gaia mission and its unprecedented survey of a billion stars in the Milky Way. And guess what? The tension is now even tenser. So, is it time to rethink all of cosmology? Before we can even think about doing that, we should probably do a refresher on what the issue actually is. So, you may have heard that the universe is expanding. Space on the largest scales is stretching, throwing galaxies apart from each other. We've talked about how astronomers first figured this out. Long story short, when a distant galaxy's light travels to us through the expanding universe, it gets stretched out. Its wavelength increases. If we also know how far that light traveled, the distance to the galaxy, then we can figure out the rate at which space is expanding, at least along the path to that galaxy. Combine the redshifts and distances of many, many galaxies, and you have the expansion rate of the universe, typically expressed as Hubble's constant, after Edwin Hubble, the guy who first properly measured it back in 1929. By comparison, getting distances to a galaxy is much trickier than getting redshifts. It depends on a long chain of distance measurements that we call redshifts. First, you measure the distance to objects in our solar system. Then you use those to measure distances to nearby stars, then more distant stars, then nearby galaxies, then distant galaxies, etc. If one of those distance measures is wrong, then all subsequent rungs of the distance ladder are off. Hubble's distance measurements were based on a method pioneered by Henrietta Swan-Leavitt. She developed one of the first so-called standard candles. These are objects whose true brightness or luminosity can be known. Knowing the true luminosity of an object means you can figure out its distance just by observing how its brightness has been dimmed by that distance. Swan-Leavitt realized that a type of pulsating star known as a Cepheid variable has a rate of pulsation that depends on its luminosity. Measure the pulsation rate and you know its true brightness, so you can find its distance. And if the Cepheid is in another galaxy, you have the distance to that galaxy also. Cepheid variables are great standard candles, but they're just stars. They are too faint to see beyond a certain distance. In the 1990s, two teams of astronomers employed a new type of standard candles, the incredibly bright Type 1a supernovae that result when a white dwarf star explodes after cannibalizing its binary partner. Using these supernovae to get distances to galaxies halfway across the universe, they found something totally unexpected. Not only is the universe expanding, but that expansion is accelerating. And so dark energy was discovered, a mysterious and ubiquitous energy that grows as the universe grows, speeding up its expansion. Dark energy very likely holds deep clues about the fundamentals of reality. With its discovery, it became very important to perfect our measurements of the expansion rate, both to confirm dark energy's existence and to learn of its true nature. And this is where our story splits. There are, broadly, two approaches to improving that measurement. One is to double down on the old method, find more Type 1a supernovae and improve those distance measures. The other is to find a totally independent measurement of the expansion rate. A good reason to do that is that the supernova method is a pretty high rung on the cosmic distance ladder. which means that if any rung below it is broken, the method fails. So,
How to
different
solve
teams of
a
astronomers
logarithm
pursue
with an
both
exoplanet.
approaches, and this is where the crisis emerged. One alternative method for getting the expansion rate is to study the oldest light in the universe, the cosmic microwave background. This light was released only a few 100,000 years after the Big Bang and carried with it vast information about the universe's early state. Now, I'll leave you to watch our previous video on the subject to see how our map of the CMB using the Planck satellite
On a foot rope,
gives
2
us the
minute
expansion
drill.
rate.
Infinity.
The Planck team
Forever.
calculated a Hubble constant of 67.6 kilometers per second per megaparsec. Let's not worry
That's a
about
great
the weird
question,
units
and it's a
right now,
question for Joe
but they
Biden,
also
for Kamala
claim an
Harris, and for the
uncertainty
leaders of the
of
Democratic
about
Party.
half a
And Biden.
percent,
And I've had many
making it the most precise
conversations
measurement
about
of the
how
expansion
the
rate
leadership
ever
of this
made.
party is
Meanwhile,
unfortunately
Adam
taking
Rees, one
our
of the
country in the
Nobel-winning
wrong
discoverers
direction.
of dark
And this
energy, has
latest
doubled
initiative
down on
of
the
this
supernova
online
method.
Do this bring
policy
back
A couple of
Harris?
years
Does this
ago,
bring
his
back
team
Harris?
published a new
You
Hubble
have
constant
that
of
thing.
73.5 plus or minus 1.5
American
kilometers per second per
rabbit
megaparsec. That's in the same ballpark as the Planck result, but far enough off to raise
There
many,
it
many
is, Cobra
eyebrows.
Kai.
One possible explanation for the difference is that the nature of dark energy has changed over time. The Planck team's Hubble constant assumes that dark energy has had a constant density for the entire age of the universe. Now that's what you'd expect for the simplest models of what dark energy might be.